Thank you again for AIT to invite me to come to share with me on some of my work. And the topic today, we're talking about parametric design analysis and design engine. Basically, it's not just for tall building, but we are particularly focused using this framework for tall building. And I will share with you with some successful example. But it can be, again, I do use it for other, not tall building, but long-span or complicated structure. In Bangkok, I just remind me that I haven't been this building even finished, but I was involved in the very early stage with Euler on doing the structural concept and so forth and so on. I'm not too old, but I still want to talk about history. Once upon a time, now I think a lot of you are very young. Probably you don't have, how many of you actually use a technical ink pen to make drawings? Wow, only two, right? I think in the past, we only use hand sketches to show how the structure is going to connect, and then we use hands to make drawings, making lines and so forth and so on, right? And later on with the computer, we start using CAD system, right? Computer-aided design, and I find personally now, I find that a lot of my young graduate engineer, they cannot draw a straight line by hand. Right? I think this is, I feel a bit disappointed because drawing is the language for engineer, especially for structural engineer. So I insist them they have to make sketches, hand sketches. Right? Don't send me a CAD drawing. so let me know how you're going to do the connection before you actually send it to the draftsman, etc. Right? And for that, for this one, they can be trained for having how to make sketches and also from a three-dimensional view. With the CAD, yes, and then from 1D to 2D, and also with the CAD system, looks like a 3D, draw it looks like a 3D. But of course, I mean, with the computer, again, we can make it like 3D, right? With all the Cartesian coordinate, we can also do the shading, we can also showing how the connection is going to connect the bolts, the nuts, etc., etc. And also because of this, it allows the architect and engineer to have a bit more rooms, right, to have a more freedom on design. In the past, we probably only column must be strict and beam must be strict, etc. But now with the computers and technologies, we can now make a bit more interesting, right? Especially for tall buildings. For tall buildings, every building are unique, right? So we have to work with the architect. And this is a very old project for me. It started by about early year 2000. And we work very hard with this architect. And he got the rendering. Very difficult at that time. It take a lot, like 2 hours to make the rendering at that time. But we do, based on that, we try our very best to make a computer model, and also we try to use, at that time, it's only like a 3D, not a BIM, right? It's only like a 3D, CAD system, etc., etc. And also with this, we can, from an architect drawing, and we have the structural computer model in the middle, and then we have the like a 3D CAD drawing on the right-hand side. At that time, we try, spend a bit of money, but I think it's worth to try. Again, this is in early year 2000. Now, we have complete BIM model, three-dimensional model, right? For the Marina Bay Sands, this is one of our examples. You can see how the podium, what is the foundation, how the tower, and also on the top, what is the sky deck looks like before building it, right? We can also show it here can see here how the structure, the roof, and so forth and so on is going to connect it, right? And it gives you an idea, how it looked like, right, before it was built. And we got a winner of the year 2010 Bentley BIM award. After that, we also, of course, we can extend it before structure. We can include the building surfaces and also other like a facade and so forth and so on, especially in airport because it's more complicated projects. And this is our Hong Kong Airport midfield development. From 3D to BIM, is it all? No, and we can also include the construction sequence so that we extend from 3D to 4D. And of course, we can also include the cost, and then we have the 5D, and also we can extend to whatever multi-dimensional project. And I didn't show you because of time, I didn't show you, but at the same time now we are integrated this BIM with a city. Right, with a city, we can now plan for the whole city, right, with all the underground utility, underground line, foundation system, building, and so forth and so on. And also we have the building shape already built on it, and we can do a microclimate study by computer, doing how the airflow, what is the air pressure in the typhoon situation, etc. But this is not our focus for today. Tall buildings. Again, all the tall buildings are unique. You can hardly find another tall building to be exactly the same unless they are, commodity government housing, right? Which is quite common in Hong Kong, but the tall building, the residential tower still have a big change from one to the other because of the environment. But you can see all the tall buildings, they have a different shape. From an architect, they're looking at more on the shape, the geometry, and some developer may be looking at the function. For engineer, probably we are looking at the system, right? Or how can we design a good buildings, right? Or good structural, from a structural point of view. With all these tall buildings, it probably happened in the last 20 years, right? All these buildings, most of it, right? And it's a rapid development is again is due to technology, right? Technology of the computer, we can calculate faster, but at the same time, we do have a lot of area that we can use the computer to help us. Computer, in the past, it looked like just making drawings, right, or plan or do the calculation. But now what we did, this is a Taipei Pop Music Center. The architect is Arup, and he is making a very contemporary design for the exterior. But every time he moves a pawn, it takes us like a day to redo the model. So what we're going to do is, because we know Arup, and so from day one, we start working with them and talk to the architect. Let's fix the software we use. Vinyls, okay, done, vinyls. And then based on vinyls, we develop our routine so that we can extract the geometry from the vinyl to a structural computer model. But at the same time, we have another library that stores all the member size, the dimension, etc., and so forth. And so that when you change the architect change the one of the node, the structural model change. And then we can do the calculation very easily. And then we can recalculate and let them know what is the revised size of structure. And this is the, based on that, we can also provide the drawings for construction. You may look it like familiar, right? Some of you may be doing this already. And then we now talk about parametric. Parametric technology is not new, and actually I use this technology in probably early 80s when I'm doing stamp metal forming. I'm a structural engineer, but in Arup, my company dumped me to Detroit to do car design. We're cold, minus 26 degrees for 3 months. And in doing the car design, also I do a lot of metal forming and so forth and so on. And metal forming, you see like stepping a piece of steel, easy. But actually you got a die. A die is called a male and female. And they look the same, but actually the dimensions are slightly different. And then you punch it, and then you form the shape. But every time you change the final product you're looking for, you have to change the male dial and also the female dial, right? So what is at that time, a company called, then developed this kind of parametric technology that link between the relationship between your final product, the male dial, and the female dial. And then so that means what you need is to change the product, what you're looking for. And then the computer will automatically generate the male die and the female die for you. This is a parametric, one of the applications of early application of parametric technologies. And then we can use this one to buildings. I know there is an architect here, there are architects here. For architect, whatever they think, oh, I just changed the floor to floor height. Why, engineer, you need to take so long to rebuild the model? But for engineer, you change the floor to floor height, you may just change one number. For example, if I got a tapered building, you change the floor to floor height, I have to change every floor coordinate, right, in order to build the model, right? So it's not that easy, right? And and that's why we take times. But now with the parametric technology, we can link between the parameter, the top and the base, right? What is the relationship and so forth and so on. And with that one, then you say you want to change the top of the building, or you want to change the floor to floor height. All the in-between data are more updated automatically. And then we can now have the updated computer model, structural model very easily. And what we need is to link all these parameters. And it's quite a time-consuming process. You need to find a way to link all the data. For the column, the bracing, I take this example. This is a building, right, with a column at the base, and then a belt truss, and then a bracing, right, all this. So you say you change the floor to floor height, you say the whole building stretch up, then all the bracing angle will be different. All the floor to floor height may be different. Or you add one more floor, and all the belt truss, can I have a 2-level belt truss? Or besides a cross bracing, can we have a V bracing? Or can we have a K bracing? All these options, how are we going to handle? That's why we build up this framework to link all these components together, right, and in a computer. For example, here is a graph show you how we're going to link. A mega column is defined by this component, a mega brace by component, and core, beam, slab, transfer truss, all these are linked together. So once we have a variable, we change it. We can change the pattern. We can change based on the same model, we change the bracing pattern to whatever we want, right? Or we can use this one at the same time to change it to like a single-story belt truss to double-story belt truss, right? Not too difficult, because once you have all these parameters linked together again, right? But the most difficult is how to link the data together, okay? You need to be, sit down, think about carefully before we start, right? Also, besides, okay, making a geometry, doing a computer model, fine, but it's not our product. Our product is at the end, we need to provide joints, right? Now, at the moment, we try a lot of software, But we don't find any software that can fulfill what I need. Personally, I say what I need or what Arup need. That's why we are not going for a tools that is commercially available. That's why we developed this framework. And with this framework, we can write our own script. We can get a whole control on the model. And then we can extract whatever floor plane, cutting with the floor, or cutting at the floor level, or cutting with the floor plus whatever, 500 millimeter, or cut it in the middle of the floor, or level, and so forth and so on, and so on, right? And also, this is still a lot of things that normally a commercial software cannot do, is how the relationship between the slab edge and also the slab thickness, etc., etc. And if you work on this one before, then you will understand what I mean. But that's why we have a script which combine all these missing information which commercial software usually don't have. And then we can combine it together with the model and make it what we want. Is it all? No. Because when we say, okay, we are doing computer model, we analysis and so forth, but this is not our ultimate objective, right? We still have a lot of objectives we need to make. We still have a lot of targets we need to do. So what we're doing is we link this model with what we call the computer design optimization tools, right? This is what we call a more general term is optimization. A lot of people think about optimization, structural optimization is to produce a minimum structural weight. This definition is not completely correct because we need to strike a balance between cost, yes. How about the architectural intent or the requirement, or what is the client is looking for? The client is not looking for the lowest cost because he wanted a better performance of building. Or the architect are looking for, I want the largest column space, right? So what are you going to do? Or how do we justify our solution is probably the optimum between structure, the architect, and the client. So what we do is, again, use similar tools. For example, here, we make a simple tools. We make a simple building as a demonstration. You see it's a straight column, straight beam with a lot of columns in the middle. Whatever you call it, 4 meter grid, 5 meter grid, 6 meter grid. The spacing of the grid, the exterior of the column, the building is fixed. So the grid in the interior column will be 3 meter, 6 meter, 7 meter, 9 meter, whatever. Who is the best? Which one is the best? So what we do is we do a couple of models, and we can calculate, see, this is the virtual works analysis. It tells us the highest, the hottest color means that it takes more force, it's more effective in control, the lateral drift of the building. So it's quite, you will see that, this makes sense because the top bit is part of building is controlled by the external frame or the perimeter. So basically it means that this beam, you will make it deeper, it's more effective to control the drift. And for this one, you can make it shallower, it won't affect too much. Of course, we can make it more columns, right? And make it more column, you say the color is more like a average, right? So in terms of structural engineer, I think we'll call it, say this one looks like better, right? But in terms of architect, they may look, I need a big window, right? It's in the seaside, in the harbor side. We want a big window. We don't want a column to obstruct your view. So what is the best? 12 meter grid, 24 meter grid, or 6 meter grid, or 4 meter grid, right? So, or on the other hand, besides that, what kind of structural system is the best, right? With all these tools, now we can generate, besides it, we can generate different column grid, different, like a bracing pattern, or maybe we could have a hybrid of bracing pattern on the bottom and frame on the top, or vice versa. And of course, we can, based on fixed exterior geometry, we can do it. Or, of course, if you want, you can make it a variable external geometry, right? But of course, we need to know, usually the architect intend or the client looking for some sort of similar exterior, right? So we can do it, and by making all this, and we can generate a lot of graph information. The first top line, the red line, tell you, say, this one is probably 100% cost. That means that, so for the structure, which is the most optimum in terms of beam depth, the percentage reinforcement, and so forth and so on. Now, you say I get the beam to be like longer, that means that we need more material. Or the architect or the client want, now I want a bigger window, I can make you, I need a longer beam but a shallower beam, a longer but shallower beam. That means that the structural engineer, we need to put more steel in it, the cost will increase, right? Up to an extent that we should make it, doesn't make sense, 200%, right? Now, but within this, we can also work with the architect and again the client, say, okay, this is 100% cost, and this is the number of column or the spacing and so forth and so on. Then here you can see that, you can have a choice of like 10 meter or 10 meter or 9 meter or 11 meter or 12 meter grid will give you the most optimum bridge between like what the architect or the client looking for in terms of spacing and also in terms of the beam depth and also in terms of structural costs, okay? So it's not just what the structural engineer think is the best, but it's a solution. I can table it in the table. We can make a discussion with the whole design team and then get the best solution that comply with all the parties are happy with. Taking another example, China Jun, 528 meter tall, and now just top out and with the facade finish, and probably one of the tallest building in the high seismic zone, with 2,500 years to 0.42 G. Okay, a building such a height and also such a shape, right? And sorry, I'm not talking about lady, but the building is just like this, okay? The building is like this. And why we do so? And we originally work with Terry Farrell for design competition. And a lot of tall building now are going usually a taper like this. But we think about, oh, okay, how about, of course, you can do an inverted triangle, right? Of course, we can get straight or we can take taper. The other way around is we make this one. And what we're trying to do is push more area to the top of the building. For tall buildings, the most variable or expensive part is where? The top of the building. Not in the middle, not at the bottom. So whatever we taper a building, that means that we are losing the value of a tall building at the top. So what we're trying is to make more area at the top of the building rather than put it in the below. Well, from a structural point of view, a lot of structural engineers say it doesn't make sense because you're putting more mass at the top, you make the more drift, you need more stiffness. But in compare with the whole cost, right, of the project, we can strike a balance again, right? Whether, how much area we put on top, how much stiffness or extra cost we need to put in the structure, which one is the best, okay? So we need to look at the form of the structure, the structural form, whether with a bracing on the top, through the top, or somewhere how many sections we have. Or say if the top is a hotel, we don't want a brace, we want a frame, how does it look like, and so forth and so on. Whether the corner, what is the spacing between the corner, how about make it chamfer, or make it circular, or how about the spacing between these two corners, Now you got so many variables, right? It's very difficult, right? So what we're trying to do, and we make it in terms of efficiency, in terms of buildability, in terms of cost, you know, okay, the client like circular, but you need to pay more. But how about I want a circular, but I don't need to pay extra, right? This is what the client are looking for. So what we did is, okay, so again, we use the parametric technology. We make the model, and we make a model, and then we can change. We can change to say the top of the tower without changing the width, or we change the level of the width without changing, and also with the variable on the top of the building. So you can come up with, okay, like this, or like this, right? Or the top slightly smaller, or the top is slightly larger. So you got so many, and then of course the architect are looking for how it look like, but at the same time, you're looking for, you know, all this, right? Making more, and the mass change, because the mass change from the CG is changed, so all this will be each option is a individual model. We link with this is just an example, we link with the corner, so that give you a condition with the spacing of the corner, then we will add a brace, or we don't have a brace, or we can add a beam, or we don't have a beam, or how the secondary beam, how the main beam, how is it going to connect, etc. Right? This is what we can do. Make it simple, all this, then you can see how many variables do we have. Right? You've got so many, right? We've got a lot of variables we need to make, and so forth and so on. And another example is how about the corner? You can see like here, the column is only 4 columns at the base, or lower zone, 4 columns. And then you split it into 2 columns. So what is the spacing between these 2 columns? What is the relationship? What is the angle? It will affect the stiffness, right? Not just the diagonal bracing. So we study with all these, we can generate a lot of model, and of course we do have some sort of equation we can use, and to generate the angle of the column, and then we can find the most optimum one, okay, related to the geometry, right? The architect looking for, and so forth and so on. And then this is another area which have been seldom done by others, is unfavorable area. What's meant by unfavorable area? Unfavorable area is the space between the column edge to the facade. For tall building, usually this space cannot be used. For this building, besides column, we have a bracing. Again, if you look at the tower is curved. That means that if we want to have the bracing to be as close to the facade as possible, that means the bracing has to be split into a lot of number of levels, right? A lot of straight line. Now, but for bracing, we should be as large as possible to make it more effective. That means that if you got a large bracing, it's structurally effective, but you got more unfavorable area, right? So what we do is we make it here, also check with the area as a function of variable. This is the area that we want to optimize. And then we generate the model, we generate the numbers, and so forth and so on, and then you end up with, at the end, based on the original, you know, the architect think about, okay, I want this geometry. Then we mix this one, check with the bracing and so forth. We save 8,700 meters square, which is about 2 floors. This is about 1 billion Hong Kong dollar. Okay, or like, I think it's 0.8 billion US, something like that, right? This is, the client once he look at it, he love it, right? Because I'm telling you, the best way you can make a structure more effective, at the same time you save 2 floors of area for tall building is lots of money. So within this limited time, in terms of design, with about 9 months time, and we generate about 854 options, right? So a lot of options, and so forth and so on, and we come up with a solution for the client and the architect. And now we start at end of the year 2011, and the building within a year it start piling. It take a year, and then now it was basically top out last year. Besides this architectural related issue, and also structural engineer, we do have a lot of challenge. And we need to, this morning, our professor talked about seismic and wind for tall buildings, etc., and also foundation. But of course, we do need to handle it at the same time. And so for doing structural engineer, when we do the design, especially for tall buildings in seismic area, we have to go for performance-based design. One of the challenge for performance-based design is we have to need to go for like nonlinear time history, because we need to know how the structure behave in 2,500 earthquake, where some of the members get yielded, right, and so forth and so on, right? And you can see this building, how it's moved. If you look at the base carefully, the actual ground is moving, because we are using a displacement time history rather than acceleration time history, which a normal computer software, commercial software will do. Because we want, there's other reasons, and because we do have other podium and so forth, we want to check the displacement, etc. But at the same time, because the earthquake actually come from horizontal movement as well. So we check, we calculate the high mode and so forth and so on. And of course, these designs that, we are more interested is on how the structure behaves during earthquake. And you can see how the plasticity is going to develop during the earthquake, right? Or during this time history record, okay? And you can see, and we can check which member first, you first, and load redistributed, and so forth and so on. And you want to change the behavior, we can look based on this result to do. Or basically, for the nonlinear time history used to validate or the performance of building we have designed for, whether it can meet with 2,500 year earthquake event, okay? And besides, this is the analysis and design engine for. Basically, but for nonlinear time history, for performance-based design, we have a different computer model because we have a different software. And also, besides this, we have a lot of analysis we need to do. Connections, subjoins, etc., etc. So we link up with this framework, cut it short. We make this framework in the middle. This is our what we call the analysis and design engine. It's a framework, again. It's not a software. It's not just a simple software. It's by means of script, module, and so forth and so on. And you can output for like a general elastic analysis model like ETAP, SAP 2000, or our in-house GSA model. You can output to a rendering, Rhinos. You can output to a AutoCAD for 2D drawing. And also we can generate a what we call the LS Dyna model for performance-based design. And also we can generate model for connection design, for finite element design, and also we can generate a shop joints, right? This is very important because again, when we design, the building design change, and the angle of bracing may change, and so forth, and all these make the connect, and all the shop joint needs to change. All the connectivity, the cassette plate, the stiffener, and so forth and so on, all these relationships are interrelated. Right? So you will change the angle of bracing, you change a whole lot. So with all this parametric technology, we can now link it together and make the life easier. Again, this one is the how we make the computer model. And actually, this is based on the global model. And then we extract this part and do the meshing. And then based on this, we can do the finite element analysis for the connections, right? For detail analysis for the connection. And then we can check the stress and also check the strain. Again, we are based on this one, we can do all the shop drawings. And then the contractor can, based on this, we can do the connections. Also, with all these, because we have the three-dimensional model in a true coordinate, etc., we can work with the columns. A lot of, for example, like column. Now you see the column. This is a drawing actually generated by the computer. This is the column at the base, 11.5 times 5.2 meter. Because this is a 600-meter tall tower with only 4 columns at the base, right? For Shanghai Tower, 6-point-something meter, but it got 8 mega column and then plus another 4 minor columns. So basically, you add together, more or less the same actually, and it's a composite and so forth, and we work, and so that this part is the exterior, it maintains unchanged, and so we squeeze this whatever hexagonal shape of the column, squeeze by level, by level, by level, by level. All this, the bracing is going to change, right? Again, we have a relationship with the stiffener, internal stiffener, etc. It generates automatically. After that, we can also, this is done by the contractor, but we give them the drawing. And how to construct the columns, this mega column. Again, this mega column is 11.5 by 5.2 at the base. You just cannot live, right? Even for 1 story, right? Can't. So when we design it, we actually design it with a consideration of buildability, what we call it. We chop the column into boxes and so forth, and so that it can live up at least like a story plus, and then they can weld it, and also make sure they have sufficient space for them to weld and so forth. In China, we prefer, in the practice and so forth, they prefer welding, so we use welding. And also you can see this is the drawing we suggest how to make this what we call the multicellular composite column. And so that they can fabricate it in the shop and then weld it on site by each 4 piece, right? This is the example. This is the on-site example. This is a worker, a labor there, and you see a big box. Okay. And so today I'll go through with you for 2 examples. One is the Tianjin 117, which is 597 meter structural top, right? And actually taller than Shanghai Tower. You talk about structure. And the other one is 128 meter China June with all these analysis and design engine. We use this one to help us to the design and also to deliver these 2 prestige projects. And we are now coming to a more and more project using this kind of tools. And this project was originally funded by Arup DTX1 5977, and thank you for the support. And also this is the end of my presentation. Thank you.